I did record last lecture. I'm going to keep trying to record them. Let's see how the audio-visual process works. I do have a new cart today, so hopefully it will hold up. And the adventure continues. Now, where were we? I lectured once. Do you have a question?
Homework is already past due?
Homework 1 is past due. So go ahead and have a seat. Homework 1 is past due. It's due at 12:30:00. So go ahead and keep it. And the reason I do this is because I don't want people coming into lecture a couple minutes late and turning in homework. So you can turn it in any time you want to early, but no time late. So now, if you've read the syllabus, you already know that your lowest homework assignment is dropped. So if you miss one, no penalties. And that goes for discussion as well. That goes for one other thing. Oh, you know what I was about to say? I was about to say that goes for online homework, but there is no online homework this semester, so that can't be dropped. Let's see. Labs can be turned in up to 1 week late with a 20% penalty. And your lowest exam percentage can be replaced with your final exam percentage if it helps you. Okay. So those are sort of part of the things. Now, I forget if I said this before, lecture. I don't award any points for coming in lecture other than hopefully it's useful, and I do occasionally give exam hints in lecture, and those are, of course, unannounced. Okay. But where were we? We were talking about this thing called combustion analysis. And here's a schematic of the combustion analysis process. You have a sample, you burn it, in this picture with a Bunsen burner, you add oxygen. And I'd written up a general equation, or a general reaction, but it wasn't a reaction that you could balance, not yet, because you didn't know the formula of the compound that you're putting in. So what I like to do is I like to do our first combustion analysis problem that we're doing in lecture. It deals with tartaric acid, the white powdery substance that coats tart candies, such as Sour Patch Kids. Really? That's a candy? My daughter loves it. I don't know. I don't know why. Oh, go have a seat. No, so homework's late. You can't turn it in. So, anyway, so you will always start combustion analysis of a 12.01 gram sample. That's our sample size. Contains only carbon, hydrogen, and oxygen. Produce some carbon dioxide, and the carbon dioxide here, and some H2O. What is the EF, the empirical formula of tartaric acid? So what we said last time was that in the unknown sample, all of the carbon goes to carbon dioxide. So you can take your grams of carbon dioxide, turn them into moles of carbon dioxide, then turn them into moles of carbon. Those will be the moles of carbon in your unknown. Molar mass of carbon dioxide, 44.01 grams per mole. Grams on the bottom, so they cancel. Moles on top. And I put this step always because it helps me think about the process and it helps me review my notes later so that they have meaning. But if you don't write the next step on your exam and you understand it, that's fine. But in 1 mole of carbon dioxide, there's 1 mole of carbon. And I think hopefully that makes sense. I'm happy to answer any questions about that. But then that's the math. And it looks sort of similar to the math that you might do for an empirical formula. You're going to moles. Although we'll also have to go to grams here. Anyway, let me put the answer up here. I get 0.3199. Moles of carbon, and I am keeping 1 extra sig fig like empirical formula problems so that my answers come out nice, neat, and clean as whole numbers. Then, well, this is Chem 400. I bet if I tell you the moles of carbon and ask you how many grams of carbon, you know how to do that. Does that sound right? It's just times 12.01 grams per mole. So I'm not going to show that step, but I am going to convert these moles into grams, and I get 3.842 grams of just carbon. And we'll do the same thing or something very similar for H2O. We'll convert it into moles of H2O and then into moles of hydrogen. What's different this time is that for 1 mole of H2O, there are 2 moles of hydrogen. And this time I get 0.4795. Moles of hydrogen. And converting that into grams of hydrogen, I get 0.4833. Where because this is an empirical formula type problem, I can't just use H by itself. I know that came up in a number of questions I got in office hours, and where H2 is the diatomic form is what we're used to seeing. But this is an empirical formula problem, and we can have just H's. Any questions so far? If not, then we have our moles to do our mole ratio thing for empirical formulas for carbon and hydrogen. We do not have oxygen. To find oxygen, we start with our sample. We subtract the grams of carbon, we subtract the grams of hydrogen, and we'll be left with the grams of oxygen. And I get 7.685. Which, I mean, 2 decimal places. Maybe I should round that to 7.69. Either way will work. And what we can do is then we can then convert grams of oxygen into moles of oxygen. And I get 0.4806 moles of oxygen. Question?
So why do you have to change it from 4 sig figs to 3 sig figs since all others are?
Yeah, you know, sig figs for this isn't really, so this is one of those problems where it isn't really going to matter. I did because I only had 2 decimal places, so, but yeah, I didn't have to at all. If you plug this number in, you'll get a very slightly different number that will still tell us the exact answer. I know, I went back to 3 and then I went to 4. I apologize for that. Sort of means that as long as you keep a bunch of sig figs for these problems, your answers will work out. Yeah, that's not a very good answer, but yeah, it'll have to be. Yeah, so, okay, so, 0.4806, 0.4795. Those numbers look very similar, but neither of them is my smallest number of moles. Now we divide by the smallest number of moles. The carbons, just 1. hydrogen, I think I get, all I have here is 1.5. And for oxygen, 1.5. So we don't have small whole numbers yet, but we have nice clean ratios. You can write it out. With fractions or decimals as part of your work, but of course the empirical formula. We'll have all of these multiplied by 2. Here is your empirical formula for tartaric acid. Any questions about that? All right, so now let's do another one. This one's a little more complicated. And this particular one, we have an unknown powder found at a crime scene. It's your job to identify the chemical formula for the substance and its common or generic name. You will find a problem on the homework almost exactly like this in format and style. The only things that are going to be different are these numbers. So let's walk you through this. Note that you have a sample size and grams of carbon dioxide and grams of water, or H2O. That's exactly like the last problem. What's new is there is a separate analysis with a differently sized sample of the same material, and you're measuring for nitrogen. So the first thing that makes this problem different is that not only does it have carbon, hydrogen, and oxygen, it also has nitrogen. So there are 4 possible elements. And nitrogen has a different sample size for the analysis. But the first part of the problem is exactly the same as we did before. We can find carbon and hydrogen based on grams of carbon dioxide and grams of H2O. And let's do that first. .9127 grams carbon dioxide. And I'm setting it exactly the same as I do over here. Molar mass, mole to mole ratio. And I'll also do the exact same thing with my grams of H2O. Ooh. Nothing on my sleeve. It's the same problem so far as we've already done. And I'll write down the answers there. It looks like we get, and this is interesting, we have 5 sig figs. So we're just going to carry plenty. Let's carry plenty, right? Who knows what's going to happen? We can always forget them later. And I get, as far as my moles of CO2, 0.11163. Sorry, that's moles of C, carbon. And turning those moles into grams of carbon, 1.3406. Same thing here, do the math, multiply across the top, divide by the bottom, 0.15781. Moles of hydrogen. And 0.15908. Now, did I do this? Ooh. Do you have more space? Oh, you guys have some space left. Good. Well, I'm going to run out of space quickly, but I'll try and keep it as condensed as possible here. In the previous problem, we found carbon, we found hydrogen, and then by subtraction, we found oxygen. First message, you always have to find oxygen last. So we need to find nitrogen first before we can do it, okay? So next, we're going to use this information to find nitrogen. So note, oxygen is always last. And found by subtraction. And we'll get there. But now let's do nitrogen next. The next thing I'll point out about this problem is that the sample size for the analysis of ammonia is different than the sample size for the other two elements. So we have to find the amount, based on this, the amount of ammonia and then nitrogen that would be in 1.8 grams. So I'm going to use what's called a scaling factor. And a scaling factor is just a fancy word for a ratio. We'll actually see scaling factors in a different context in lab number 2. So look for that. It's a useful thing to do. But it goes like this. If I have 0.0182 grams of ammonia in or per a 0.5 gram sample, and I want to put it on the same size sample as my carbon and hydrogen with this 1.8 gram sample. I can set up a ratio, cross multiply, solve for x. X will be my grams of ammonia. And I get 0.06552 grams of ammonia. From there, the next thing I'm going to do is inside the ammonia, I'm going to find my grams of my moles and my grams of nitrogen. So I use the molar mass of ammonia. And then in ammonia, for every 1 mole of ammonia, there's 1 mole of nitrogen. And I get 0.00 3847 moles of nitrogen. And a corresponding number of grams of nitrogen, 0.05390 grams. Any question about the scaling factor? Or about what we're doing with this nitrogen now. So now we have our moles of nitrogen. It's comparable because it's on the same size sample. Last but not least, we're going to find our grams and moles of oxygen, and then we can do our whole ratio thing in these elements. So now we're going to find O O is the exact same process. Start with your sample. Everything's in terms of the 1.8000 gram sample. Subtract off your grams of carbon, grams of hydrogen, and grams of nitrogen to find grams of oxygen. And I get 0.2464 grams of oxygen. Now I'm going to set up the same thing over here. Leo, question?
So, how can we find the hydrogen if ammonia also has hydrogen in it? Like,
Great question. So we found hydrogen up here,
okay.
and then there's hydrogen down here. Okay? So we won't say too much about this process of finding the nitrogen, other than to say you take a sample of the same stuff and you add hydrogen to it. And because you add hydrogen to it to make this ammonia,
Oh, okay.
you can't balance the hydrogen using this number.
Got
That
it.
makes sense?
So that hydrogen is added and not part of the original.
Right. The whole point of being able to use this, the water, the H2O, is because all of the hydrogen from the sample goes into that compound when you do combustion. So that's why. Does that answer your question?
Yeah, that answers my question.
This process will only work for nitrogen. We will see other possible elements. And in those elements, it will always, so in one that we do is chlorine. And then in chlorine, I will have to tell you what the chlorine compound is and the relationship to do this stuff. So there's a couple of variations on this, all of which are on the homeworks. So you can see just what we can. Good question. Any other questions about this? Yeah.
When you say variations, you mean sort of like the calculations and analysis and such things, that's the same process.
Same process, yes. This process is very general. In order to help to tell me that you understand how the process works, there'll be a different type of problem, and I forget exactly which one's on the homeworks this semester, but there's one with chlorine, there's one with sulfur, and one with phosphorus. And for chlorine, I say you do a separate analysis, and let's say you make Cl2. And then you can figure out the grams and moles of chlorine from that. So does that answer your question? Yeah. I mean, that's you know, honestly, the scariest thing about the exams is I'm not giving you the same problems, but they're not that different either. So anyway, but you can also see that there's definitely some reading skills here to figure out what's going on, some tables of data, and so you got to pull what you need. Well, we were down here with oxygen. We were converting it into moles. And we get 0.0154 moles of O. Moles of oxygen. And so now we have moles of oxygen, moles of nitrogen, moles of hydrogen, and moles of carbon. There are a ton of numbers in this problem. Very easy to get the wrong number as you go. Organization is critical as you solve this problem. I'm going to reorganize down here. And actually, I'm going to reorganize up here because I'm sort of out of space. And I'm going to write C to the subscript 0.11163. h to the 0.15781, n to the 0.003847, and O to the 0.0154. This step for me now puts all the numbers in one place. I can see which is my smallest one. Incidentally, the biggest problem I see on these problems from student work, and I do it sometimes too, is you drop a 0. And then if you change this to 0.03, all hell breaks loose. But you know that hell is broken loose. Well, it's certainly warm enough. But you know because you don't get small whole numbers when you solve the problem. You know when you solve this problem correctly because everything is small whole numbers. All right. So this is the smallest whole number, the smallest number here. Divide everything by it. And again, you don't have to show all this work. I like to, though, certainly when I'm doing my homework. And what I get here is C29.02, H41.02, N1, O, 4.003. Yes, that is, well, we're pretty close to, so I don't know if they count as small whole numbers anymore, but they look like whole numbers. And when you solve this problem and you note that there's an extra sig fig or two, that is to make these numbers work out as precisely as they do. So you can tell that this is 29. This is our empirical formula. Is this our molecular formula? Could be, could not be, right? We've been given the molar mass to about 468. If you do the molar mass of this beast, you will find out that it is very close to 468. And it is the molecular formula. Always check that. And then in the problem statement, and I always suggest that after solving one of these problems, you go back and you say, I have the chemical formula, that's going to be the molecular formula. And now I need to look up its common or generic name in Google. And you can do that and you will find what this is. Any questions about that? The new things are the scaling factor and having to deal with nitrogen. With that, I think there's one other problem. And then we're done with lecture 1. I will say this. We're into lecture 2, and I didn't finish lecture 1. I will go sequentially through all of my lecture notes, regardless of where I start and stop. Every semester is a little different. Now it's, who does not have the People's Guide and needs a copy of today's lecture notes as I continue? I brought 20, thinking that several people would have it. So I'll tell you what. Mariana, would you pass them out to the people that raise their hand and keep one for yourself while I get the next lecture up? Good. Question? Yep. Are those online? No. So you have to buy the People's Guide to get them from now. Does anybody still need one? Yeah. Question. You can buy those at the bookstore. I checked on Friday, and they had plenty. So, how much is it?
I think it's $38 or something like that.
38
And
bucks.
it's just called the 24 on the It's in the, if you go to the bookstore, they got in the class or
It looks like this. I finally got mine. What does that say there? Chemistry-related Halloween costume contest? Huh. So, do you think I offered extra credit for it? With that kind of turnout, I bet I did. Well, Halloween's still a little bit away, but one of the great things about teaching this in the fall and taking in the fall is we will do that again. And I'll just sort of throw this out there, maybe to give you time to think. Everybody who wears a costume gets 5 points of extra credit. The winner gets 10. And their extra credit max goes up by 5 more. So if you're, oh, and this is a good time to talk about this too. So study groups. If you're going to do a study group, start this week. Plan on meeting every week and plan on documenting what you're doing. A study group, I will allow study groups to be as small as 2. So if you're in a study group, that puts, you get 10 points for doing it, plus your extra credit limit goes up to 15. If you're not in a study group, your extra credit limit is 10. Say you're in a study group, there's 10. You get to do one other thing, there's 5 more. You do the Halloween costume contest and you win. Your max is 20. And you're the only one in the class that can do that. Well, we'll see. Anyway, so hopefully, anyway, I don't know what hopefully, but let's talk about where we left off. And we're doing our next lecture. And we're going to start here. It's called How to Read and Write Chemical Equations. They aren't called chemical equations. I tend to call them chemical reactions. They're equations because the stoichiometric coefficients are related. I'll refer to them both ways. All right. So our first reaction type is a combustion reaction, also called burning reaction, also called complete oxidation. Now, if you're familiar with how many different terms that Eskimos have for snow, you realize how important oxidation, combustion in this process is if we have a number of different names for it. This is an important process. And so combustion of propane, when it says our first reaction type, that means I can ask you to write this reaction on an exam. And we'll go over it many, many times. A combustion reaction always looks like this. Something is being burned, or something is going through combustion, plus oxygen, and then oxygen is a gas, goes to carbon dioxide and H2O. And I'm going to put H2O gas there. Some people put H2O liquid, but I would suggest that most combustions occur at high enough temperature that H2O is a gas. And this will become important actually when we get to chapter 6, whether it's a gas or not. Now, propane is this compound. However, when you balance reactions, it's always easier if you get all of the carbons together and all of the hydrogens together. And so I'm going to write it as C3H8. That makes it easier to balance. And anybody ever done Mad Libs? This is the thing to be burned. And it doesn't matter what it is, but I could say, write a combustion reaction or write a burning reaction for propane. I could say, write a combustion reaction for C9H22O4. And you would do this exact same process. Now what do I mean by that? Well, there's the reaction, but is this balanced?
No.
This is not a balanced reaction. My balancing process, although balancing is largely a Chem 300 skill, we will get to practice it. I always put little lines here and for the coefficients. And then when I have all the coefficients complete, then I'm done. There are lots of ways to balance this reaction, and I am open to all of them. But I'll show you my way. I put a 1 here next to the most complicated thing. And then if there's 3 carbons here, there must be a 3 coefficient there. Because carbons are only in one place on each side. What does the coefficient of water, or H2O, have to be to get 8 hydrogens? It has to be 4. Now, oxygen is an element by itself. If whatever number I put here, it doesn't throw off any of the other elements. That's why I do it last. And
5.
It has to be a 5. That gives me 10 oxygens on the reactant side. 3 times 2 is 6. Plus the 4 in H2O. That balances my oxygen. So, how many people balance reactions in a different way? By, say, adding up the atoms of each element on each side. How many people balance reactions in when they took Chem 300? Hopefully, all yeah. All right, well, so let me take you through my process, or my guidelines as I'm calling them. 1, use lines for coefficients. Put a 1 coefficient in front of the most complex formula. Balance each element in most complex formula. Three, balance 1 element formulas last. And the example of the 1 element formula is O2. And something we didn't do in this example, which we will in others, is if there are any fractions, clear fractions. Combustion of ethane. Now seems like a very appropriate time to talk about what's going to happen next week in discussion at the beginning. Discussion, remember, is the 2-hour block of time, and if you look at your syllabus, it says, next week in discussion, limiting reactant quiz, nomenclature quiz, solution, stoichiometry, and electrolytes. So here's what's going to happen when you come in next week to discussion. You will have a limiting reactant question just like the last problems on homework 1. If you remember the homework 1 problems, it said something like how many grams of product can be made. You have given 2 grams of reactants. It's not supposed to be hard at all. It's just supposed to make sure that you know how to do that. And I believe if you check the Chem 400 website, there is a practice quiz there already. If it's not, let me know and I will put it up there. Because the way I do quizzes is you will get a similar wording, similar problem to do as practice ahead of time so that you feel comfortable by the time you get to the quiz, as comfortable as possible. There will also be a sample nomenclature quiz there. The nomenclature quiz is based on the nomenclature sheet in the People's Guide, also available on the Chem 400 website. It will say at the top, 11 ions, 2 common compounds, and 2 elements. That's a total of 15 questions. It's a 15-point quiz. And they're all on the nomenclature sheet in the People's Guide. So, but you'll see an example there. There's no compounds. So for example, you could be asked to name Na plus or Cl minus, but you cannot be asked in the first quiz to name NaCl. Anyway, we'll see it. That quiz also is meant to be a check-in and establishing, okay, we know all the Chem 300 stuff for enough of them. Any questions about that? Well, when you do, you'll see that on the list of common molecular compounds is ethane. On that list, it's listed as CH3CH3. When we write a combustion reaction, I'm going to suggest you write it as C2H6. Question?
I have a question about the balancing equation. Is the one like sort of redundant, like you don't have to put it there?
Oh, good question. Is the one redundant? For sure.
Okay.
Yeah. I would say the only reason I put a 1 there is because I know I'm done when I have numbers in front of all of them. Okay? But no, you can do it entirely differently. As long as, so the 1 doesn't have to be there. It should have 5, 3, and 4, and whatever work you need to get there. And for this particular problem, if you need to show no work, I'm okay with that. Okay. Any other questions? All right. Well, just like in this one, add oxygen to your products or carbon dioxide and H2O, and then worry about balancing. Like so. Pretty much whenever you do a combustion reaction, the thing that's being burned is the most complex. You put a 1 right here that allows you to do your carbons and your hydrogens. Now what number goes in front of the O2? 7 over 2. Because I have 2 times 2 is 4, plus 3, I have 7 oxygens here. I need 7 oxygens here, but oxygens come 2 at a time. Now we have a fraction. This is not our final answer. I've put the phases or states in there. You probably don't have to do that, or you don't have to do that if you're balancing the reaction. We'll save these, actually, yeah, we'll save these 2. These should be fine. for companion problems, so practice those. Any questions about the work we've got up there now? Yeah.
Is combustion only if it releases carbon dioxide and water? But it says combustion of nitrobenzene is another product.
Yeah, well, why don't we do this one? So I would say this, if there's another element, I have to tell you what it forms.
So it's still considered combustion even though it has some other products in there?
Yes.
Okay.
Yeah. Combustion or burning. I mean, really, in the general sense, combustion is have a heat source and add oxygen. I'm trying to think if there's other ways to do combustion. I mean, you could burn things in the presence of other things. Like you could burn something in the presence of nitrogen and see, like there's other ways, but it's not typically how it's done. Does anybody want to see me do this one? Yeah. Let's do that one. Still only adding oxygen. Now we have carbon dioxide, H2O, and nitrogen dioxide. However you balance it is fine with me. I'm going to put a 1 in front of that very complicated looking thing to me. Then I automatically know what has to go in front of my carbon dioxide and what has to go in front of my H2O. And what has to go in front of my nitrogen. On the left-hand side, there's 1 nitrogen. There has to be 1 nitrogen. Like in so many of these, nitrogen or oxygen is the last thing that we do. We'll do this last as well. I know, I'm sure this is in my notes, but I'm going to try and do it. There's 12 oxygens, 2.5 oxygens, 2 oxygens. Is that 16.5 oxygens? Oh, yes, but I have 2 right there. So I need 14.5 oxygens right there. Oxygens come 2 at a time. So I can put 14.5 over 2, which is also 7.25. But what I can see is this is a quarter number. I have to multiply everything times 4 to get small whole numbers. And I'll do that in red. And when I do that, I get 4 nitrobenzenes. Plus 29 oxygens goes to 24 carbon dioxides, 10 H2Os. Plus 4 nitrogen dioxides. So big numbers, process is the same. I would say that this is certainly the most complicated version you could ever see on preserving or an enzyme. Any questions about that? Okay. Well, let's keep going. I know we have a limiting reactant quiz next week in discussion. But we're going to do it, and we're going to do a problem to help you prepare for it anyway. Anyway, of course we will. Here's the problem when 123.4 grams of propane and 247.3 grams of oxygen are allowed to react. How many grams of carbon dioxide can be formed? What is the limiting reactant? How many grams of the excess reactant are left over? Okay. How many people feel pretty comfortable reading this problem like they could solve it? Good. Well, we're going to go through this in gory detail. And then what you're going to find is that throughout the rest of the class, we're going to do at least or greater than 50 more limiting reactant problems. And so we might as well get used to them. That's why we're doing this, is to make sure we're all good. All those 50 limiting reactant problems will start involving gases and solutions and other things. We do this a lot. General process looks like this. So they will react via combustion. This is propane. We wrote the combustion reaction for propane a couple slides back. I'll put it up here. Propane plus 5 moles of oxygen goes to 3 moles of carbon dioxide and 4 moles of H2O. And the first thing you're going to do is you're going to start with grams of propane, convert it into grams of carbon dioxide using stoichiometry. We'll use the molar mass of the propane, then the mole to mole ratio. Oh, hold on. What am I doing here? There we go. And if you've taken 300, chemistry 300 here, then even if you don't have the same format, you're very familiar with this process. We'll do the same thing for the oxygen. And I will point out to you, I've gotten this question a couple times. We're back to O2. Empirical formula problems can have O's, but whenever I give you a chemical reaction, you're 99% of the time only doing the molar masses of the things in that chemical reaction. So that's how we know we have O2 here. We're doing the molar mass of O2. We're doing the mole ratio for O2 and carbon dioxide. And one of the things you can see is that last step for both of these is the same. You can only do it once if you want to. That's fine. Again, many ways to solve these. For the top calculation, I get 369.5. units on that, grams of carbon dioxide. For the oxygen, I get 204.1. Grams of carbon dioxide. My question for you, how many grams of carbon dioxide can we really form? 204.1. It's always the smaller amount, because that's when we run out of oxygen, and oxygen is our limiting reactant. Any questions about that? All right, so let's see. What is the limiting reactant? Check. How many grams of carbon dioxide can be formed? Check. Now, how many grams of the excess reactant are left over? So that's what we'll tackle next. The way I solve these limiting reactant problems is I always come back to the limiting reactant itself. It is used up, it does react. You can do stoichiometry with this to any other thing. I could, in this case, take the grams of oxygen and end with grams of propane that are reacting. First step's the same here, then a mole ratio to propane. And it's a 5-to-1 mole ratio using the coefficients. And then for propane, I use the molar mass of propane from before. When I calculate this, I get 68.15. Grams of propane reacted away. Which is good. When I say it's good, I mean the fact that since this is the excess reactant, the amount that I start with, and it must be more than the amount that I reacted away if I'm going to have some left over. So now, to answer the question, how much is left over, I set up a little table. Started with 123.4 grams of propane. Reacted away 68.15 grams. Subtract to find the amount left over. And I have my leftover. 55.3 grams of propane. Now, on your quiz next week in discussion, you do not have part 2. Because we haven't done it 50 times in this class yet, or certainly 10. You will have part 1. Question, Shay?
Is it just gonna be one limiting reactant problem that you answer and then we're done, or is it gonna be all of those on the quiz?
Good question. When you look at the sample quiz on the Chem Fronter website, you'll see it is one problem. You'll probably get 15 minutes. When you turn it in, you'll get your, well, I probably do the nomenclature quiz first because people, that'll be fresh in their memory. You'll have 15 minutes for that. You'll turn it in, you'll pick up your limiting reactant quiz, you'll have 15 minutes for that. That'll be the first 30 minutes of discussion. And then we have a separate assignment for the hour and a half that's left about solutions. Keep those questions coming because you want to answer any quiz and exam in this class with as much information about what the content is as possible. Happy to answer. Yeah?
For finding the amount of reactant that was used, I took a ratio between the oxygen amount and the propane amount that was used, and then doing a ratio between those two, you're able to find the amount that was reacted away, and then just do that rather than going through the process that you used done.
Yep.
Is that allowed on tests?
Of course. So, in fact, I mean, one way to think of Chemistry 400 is, like, if you have, and you have plenty of knowledge from 300 or any other chemistry class, you have to find a way that you're comfortable getting the answer. It does not have to be mine at all. In fact, I present just one way to do it. And there are lots of ways, including not doing this stuff, finding moles and then doing 1 gram calculation, doing ratios. I've seen students who, when they do the molar mass, they include the coefficients. So there's lots of ways to do it. And I'm happy to say, after 20 years, I think I've seen them all. I'm always open to finding a new technique. Right? And when I started, I would be like, oh, this is cool. As always, you know. Anyway, every once in a while, people find new ways to do problems. And I love that. I'm like, great. I've learned something new, too. Especially since I make up all new problems for my exams. So, anyway, any other questions? Yeah?
This is off topic, but I just popped in my head. When's the lab that we do?
When's lab due? And this is general, so you had lab this morning. It's due by noon or the end of your next lab. For people who have lab on Monday at 2 p.m., yeah, their lab will be due at 6 p.m. on that Monday. So it's always the week after you finish it. I will say this too, as a reminder, lab 2 is a 2-week lab. So you'll have 2 weeks in lab, and then the following week after that, you'll turn it in. Any other questions? Cool. All right, then, what is the percent yield? Let's do that next. Find the percent yield. Suppose that only 167.3 grams of carbon dioxide are recovered when the same amounts that we talked about before So that's the number of grams we calculated from before that we can theoretically make. This is called, so, from previous calculations, (204.1 grams carbon dioxide is the theoretical or calculated yield. Unless you're in the lab, I have to give you the actual yield. And percent yield is always actual over theoretical times 100%. I'll write that out. Percent yield is actual yield over theoretical yield. times 100%. Plugging in the numbers, we've got 167.3 grams carbon dioxide over 204.1. Which is 81.97% yield or 82.0% rounded to 3 centimeters. Okay. Questions about that? Can the percent yield be greater than 100%? No. It cannot. Can percent error be greater than 100%? Yes, it can. There's one lab where invariably it is. As we will see, and we'll talk about that as it comes up. All right. Next problem is a companion problem. You'll find the answer already on the Chem 400 website. The whole thing, both pages, 6, 7. So we're going to go to page number 8 and then page number 9. And we'll talk a little bit about limiting reactants in everyday life. These are pictures of a Bunsen burner with different air to fuel ratios in combustion. So this is going to be methane. Plus oxygen going through a burning or combustion reaction. In the blue flame, well, and even before I go further, which of these flames is the hottest flame? The blue flame is the hottest. And it's actually the tip of the flame that's even the hottest part of that, or the tip of the inner blue cone, which I put it about right there. That's a squiggly equal sign, which means approximately 1600 degrees Celsius. This one, approximately 1100 degrees Celsius. That's a big difference in temperature. This one, oxygen is leaving the reactor. And we won't say too much more about it, but I just want to give you a flavor that limiting reactants actually do have relevance in many aspects of life. And one of the goals of, if not this class, but certainly the next semester, is that by controlling the amount of reactants, you can actually get either of these to be limiting. So, anyway, that's all I wanted to say about that. Another case where limiting reactants come into play is aerobic and anaerobic respiration. Aerobic, oxygen is present in vast excess. This is not a biology class. I have a lot of respect for biologists, but no talent at biology. So if you were to say aerobic respiration, this is how I think of it. Yeah. And there's a lot more to it, of course. What's interesting here is depending upon the ratio of actually glucose to oxygen, or where there's insufficient oxygen, you can get different reactions to occur. And here, the limiting reactant is glucose. Here, there's no oxygen even present, so oxygen can't even participate in the reaction. Which do you want to occur?
Top one.
The top one. This one maximizes the amount of energy from breaking down glucose. Wait a minute. Does this look like a combustion reaction? Yeah. Well, and what I would say is, from a chemist's point of view, that's what aerobic respiration is. So I'll just point out that this way of doing it with oxygen gives your body the most energy. This way produces a COOH group. This is the first time in this class that I think we've seen a COOH group, but it is not the last time. You will see this group greater than 50 times this semester. Let me circle it. This is what's called a COOH group, also called an organic acid group. Or a carboxylic acid group. And yes, the word boxy is in there, that's a lie. This group is very important this semester. That's why I say but this is an acid group, and what you're doing when you have anaerobic oxidation is you're making acid. That acid builds up in your muscles and can cause pain. All right. So those are two examples of limiting reactants. A third example of a limiting reactant involves lab number 4. We'll just mention this now. We'll do this reaction. We'll have grams of magnesium and milliliters of hydrochloric acid. This question you'll be able to do next chapter. We haven't talked about this, but we will. So come back to it next chapter. In the time that we have left, which is about 5 minutes, we will do a little bit of review of nomenclature. Binary molecular compounds of 2 nonmetals. There are many possible combinations. To name these compounds, you have to know your number prefixes. For your number prefixes, perhaps you've seen 1 through 10. 1 is going to be mono, as in carbon monoxide or monoxide. Di, tri, tetra, and penta. All the number prefixes, and these are prefixes, so they have little dashes because they're attached to the rest of the word. Hexa, hepta, octa, nona, and deca. Now I've left one box blank. That one box is only for hydrates. Hydrates use all of the same number prefixes as the binary molecular compounds, plus 1 more. That's because it is possible to have a half in a hydrate, and it just is hemming for half. So I'll only do a couple of these, but to give you the idea, first one, NO, nitrogen monoxide. What I'll point out about the nitrogen monoxide is that when there is one of the first compounds, there is no mono or no number prefix. One of the first compound, no number prefix. The other thing I'll say is that when you have OO or AO, the first letter is dropped. So it will not be monoxide with two O's, it will be just monoxide. Similar thing here, there's two of them now. This is going to be dinitrogen. And this time there's an AO, it's just tetroxide. We drop the A. Tetroxide. There are other ones for you to practice then. We will stop there for today. I have discussion in this room for those of you who are sticking around. I will stick around as well and be happy to answer any questions. If you did not get homework number 2, it's available right here. Come on up.